To introduce our presenter for today's training, Mr. Jason Frank. Jason is a senior project manager and Southeast Aviation lead with Garver. He's a graduate of a small school in a cornfield in central Illinois, the University of Illinois, with a bachelor's degree in civil engineering. Over the course of his 26-year career, he has served many roles, from designer to senior project manager on a variety of airfield projects with up to $100 million in construction. Those projects have included airfield reconstruction and rehabilitation projects at Bush Airport, Chicago's O'Hare, Ronald Reagan Washington National, Indianapolis International, Dulles International, Lambert St. Louis International Airport, and other civilian airports nationwide. He's also done some work with the U.S. military, including projects at Fort Bliss in Texas, Fort Benning in Georgia, McConnell Air Force Base in Kansas, Andrews Air Force Base in Maryland, and Bagram Air Force Base in Afghanistan. His experience requires him to have knowledge of FAA advisory circulars, the military's United Facilities criteria, and ICAO standards. His experience of working on airfields with a wide range of complexity gives him the understanding and the unique challenges the airfields face when undertaking improvement projects, as well as what steps need to be taken to mitigate construction impacts to airfield operations. In today's webinar, we're going to have a brief introduction to airport design and some of the challenges during construction, which I cannot imagine are minor. So, Jason, I'm going to turn it over to you and looking forward to hearing what you have to tell us.
All right. Sounds good, Ryan. I appreciate it. Hopefully, I think everybody should see the title screen right now. So we'll get started. And as Ron said, just be a brief introduction to airport design. I know some of you highway guys are always wondering, hey, what do you airport guys do? Your job is pretty easy, but we have a lot of fun, but we've got a lot of things to put in it, just like you guys on the roadway. So here we go. Since I'm here in Houston, of course, I've got to brag a little bit about the two airports we have here, Bush Intercontinental and Houston Hobby. As you can see on the screen here, quite a bit different configuration for each one of those airports. You see Bush on the left, you see a lot of 3 parallel runways and a crosswind there in the north, we'll call it the northwest corner of the picture. And Hobby is more the traditional old school kind of crossbuck design. So we'll kind of touch on those as we go through the presentation today. When it comes to airport design, there's 3 regulatory agencies, major agencies that deal with airports. Of course, there's the Federal Aviation Administration that we all know and love. We have the International Civil Aviation Organization, which is basically everything outside the United States is kind of governed by the ICAO standards. And of course, we have our friends at the Department of Defense. Each one of these regulatory agencies has their own, what I like to call Bibles. These are the go-to books where you need to start when it comes to the airport design. FAA has what they call their advisory circulars, and their main Bible is the 5300-13. So this is the basis of their design, and from there, everything else branches out from that. ICAO's calls theirs the Annex 14, and as Rhonda mentioned, the DoD, it's United Facilities Criteria, the UFC, for airport and heliport planning and design. Hopefully you can see all this. As I mentioned, the 5313, which is airport design, is kind of the second item on the list, and everything branches out from that. You see it's quite an extensive list, from drainage, layout plans, master plans, signage, terminal facilities, AWAS, pavement design. It's quite, like I said, the extensive list, several ACs that all kind of go in and mesh into to airport design when it comes to the FAA. Jumping into runway design, each of the different agencies kind of have their take on how they design the runways. For the FAA, it has to do with the aircraft approach speeds, based on the size of the aircraft, and each is divided into different design groups, and that's based on the wingspan, tail heights, main gear, and also if there's a rotary wing aircraft like helicopters. ICAO, it's based on the field size, length, and aircraft size. So say I've got 8,000 feet of runway here. what kind of size airport can I bring it into, and then they've kind of divided it up into that, and they call it what their aerodrome reference codes. So again, it gets into the length of the runway, the wing speed, wingspan, and wheel span is what they call it of the aircraft, and of course, rotary ring aircraft. The DoD and the UFC is kind of split into three different areas. We have the light aircrafts, I'm sorry, which they call the Class A's, the high performance aircraft, which most of us are familiar with as the fighter jets, and are the Class B's, and of course the rotary wing aircraft, which gives it to your Black Hawk helicopters and such. Here, as I mentioned in the FAA, we're talking about the aircraft approach category. Approach speeds are divided into 5 different categories, A through E, with speeds at A, where anything that's less than 91 knots, and then from 91 to 120, 121, 121 to 124, 141 to 166, and so on. So you see, it's quite a big range of approach speeds that come with the different aircraft. So you're basically going from your private planes, your Cessnas, all the way up to your big guys, your 787s and A320s, those size aircraft, 737s. Again, in the next item that goes onto that list is the design group, and as I mentioned before, that kind of goes into the tail height and the wingspan of the aircraft. So when you get to the design, you'll have an A2 or a C3 or a C4. It depends on where that aircraft kind of falls, both in its approach speed to the airport and also its tail and wingspan. ICAO, they're of course in metric, because we're about 3 countries in the world that do standard and everybody else is in metric. So it's kind of a similar thing. They have their field length, they don't use the approach speeds, they've kind of uses the field length, how much field length that you have there, and that's divided into 4 categories. And then you have 6 categories when it comes down to letter codes for your airport, both in the for your airplane, I'm sorry, when it comes to your wingspan, and again your outer main gear wheel span. So that's basically from edge of wheel gear, to edge of wheel gear of your aircraft. And I think I've got a next photo. Yep, here we go. Here, this is the classic 747. The old lady has been recently retired over the last few years. Not many commercial airlines are flying these anymore, other than for cargo. But you can see here we've got the wingspan, and MGW stands for main gear width, and this is kind of what falls into the ICAO standard. On the bottom of it, you have the length of the aircraft. But we have the CMG, which is cockpit to main gear. So that's the distance from the cockpit to the center of the main gear, and the wheelbase is considered from the nose gear to the main gear. And that all kind of comes into play when we're looking at more the FAA design standards. This is just kind of a fun little slide that you can see just the different size of aircraft here. Airbus, Boeing, McDonnell Douglas, some of the regional jets a lot of us fly around the state on, the CRJs, the ERJs. Of course, our friends at the Southwest Airlines and the Boeing 737s. They're on the far left of the screen. So you can see there's varying sizes when it comes to the aircraft. Is I think the chart on the right side of the screen gives a good example of just the sheer size of some of these aircraft, and even bigger when you get into some of the Antonov 175s. It's a huge cargo plane. I think most recently was flying around at I believe at Austin, landed here recently. So huge aircraft, a lot of things to look at when we're coming in on this design. Getting into the DoD, you can see here Class A, Class B runways I had mentioned before. Class A runways is typically a lot of your smaller stuff, your trainers, a lot of your prop aircraft. They do list the T6 for the Navy, which is their trainer under Class A. Then Class B, you see your more commonly known aircraft, your C5s, your KC-135 strato tankers, your C-17 cargo aircraft, all the way up to some of your fighter jets, F-15, F-16s, the new F-35s. These are all the high performance aircraft that are rated under Class B. Also listed under Class B is the T6, which is the Air Force version of that aircraft, is considered a high performance aircraft. So yeah, so you go, okay, how do we know which way to point our runways, I guess? All aircrafts take off and land in prevailing winds. So you're always taking off into the wind, you're always landing in the wind in order to provide lift for that aircraft and also to slow it down when you are landing. In order to do that, the winds must be analyzed. They take the typical data from a certain period, a record. For example, this record was taken from 95 to 2004 of hourly wind speed observations at an airport. It says it's just a generic list here. And the goal is to get 95% coverage based on these operations. So 95% of the prevailing winds will be covered by the direction of this runway. In this case, it's a runway with a crosswind component of 13 knots. So it's a little bit, smaller, or an airport that could take a little bit, doesn't want a high crosswind component. So we want to make sure we're covering at least 95% of the wind in that direction. And what will happen is they'll put a template down on what they call this windrows analysis, and they'll plot the data, as you can see there on the right part of the screen, of the percentage of winds coming from each direction based on that record. And what you see in blue is that template, and it's widened out to the inner lines are kind of the 13 knots from center each way to make sure that it is covered. And in this case, this is basically kind of as the true north and south goes. It goes from 90 to 270. So that's based on true north wind direction. Now, when we actually number the runways, that is actually based on your magnetic north. So even though in this case you can look at the compass there, it says, okay, it says 90 degrees and 270 degrees, well, that'd be a 927 runway. But because of the location of where the airport might be at, it might be a 1028 as shown in the example. Now, if we can't get the 95% wind coverage based on the weather operations, that's when they'll go in and construct look at a crosswind runway. Hey, do we need to put one in? And again, we'll do the same thing with the crosswind component, see where we can gain more coverage and align that as the crosswind wind runway. As you can see, I've put that kind of in red. This example didn't really come with something that shows a crosswind component, so I've just kind of drawn that in for just for discussion. Some interesting layouts here. This is over the airport diagram for Phoenix Sky Harbor Airport. As you can see, everything pretty much looks east and west for the most part. Their runways are oriented in such as there's 725 left and right, 824. So it's pretty much an east and west airport when it comes to the prevailing winds there in Phoenix. Another example here on the left, you probably couldn't recognize it if you tried, but this is Orchard Douglas Field. What was a potential layout for Orchard Douglas Field, or ORD, or as we know it today is O'Hare International Airport. So this is kind of wild here. This diagram that I came across many years ago of this proposed layout for O'Hare, but the idea was not to really have any crossing runway. So they thought maybe this pinwheel design would be interesting. Again, that was really kind of before they started looking hard at, hey, we really need to pay attention to which directions these winds are coming in. So on the right-hand side of the screen there is kind of what O'Hare Airport was prior to the modernization program, which began back in the mid 2000s. So this is roughly 2004 timeframe. And what each of the red dots represent is just an area where these runways cross. So the big issue at O'Hare, of course, has always been capacity. Of course, it's in my home state of Illinois. Chicago is known as the Windy City, and the airport there is no different. So they were always having issues with weather, and because these crossing runways and the winds, it kind of reduced their capacity, especially during poor weather. So they had roughly 8 different runway crossings, so they couldn't bring as many aircraft in there during reduced weather conditions. The program had just finished up recently, or officially finished up recently over the last year, and they have reconfigured the field. As you can see now, there are 6 parallel runways and just 2 crosswind runways as compared to what they had before. This is to bring in the efficiency. So now they can bring in an aircraft, both recover and launch from either side of the airfield, depending on what the traffic flow is that day, east-west or west-to-east, and they've reduced their kind of crossing runway spots from 8 down to just 3. So it's a big improvement for O'Hare, especially an airport that at the time was 1994 was peaking out around 992,000 operations in 2004. So an operation is a takeoff and or a landing. So that's a lot of aircraft when you start coming through a field. You're basically launching or recovering an aircraft once, 2 every second or so. So so they really need to made improvements on this airfield because of the weather conditions that were out there. And this for me was an interesting project because I worked on the 9 left 27 right, the northern airfield, and having to basically see the whole program and design an airport, a busy airport, and build a busy airport inside of an airport that's already active is just a real nightmare in some places, but challenging in other. I just consider them challenges because it really made my job a lot interesting on how to move the aircraft around the field, move construction around the field. So it was a fun time up there for my couple of years I was on the modernization program. Really enjoyed it. The photo on the right is near recent aerial of what the field looks like. You can probably see just be up above International. They still were doing a little bit of work fixing out finished out the taxiways for the last parallel. So moving on, airspacing. You can see the airspace. This is kind of just the imaginary surfaces that go around the airport. This is really based on the runway elevation and runway center line. What you kind of see in this isometric view is basically imagining that the runway is kind of bisected vertically. So we have this airspace where we have these approach surfaces that come at 50 to 1, 40 to 1, 40 to 1, and can go out from anywhere from 5 to 10 miles, so 5,000 to 10,000 feet roughly from the end of the runway. So that kind of helps to keep the space clear and know what we have in the airspace as an aircraft is approaching the runway. We don't have to worry about coming into the runway, but also what's along the sides of the runway. So you'll see what they call these transitional surfaces, or these kind of surfaces that are going up at angles at a 7 to 1 slope here. I know it's a little rough to see that drawing. But again, that's a way to keep if we've got any penetrations to that airspace. So the idea is to clear as much space out as you can around the airport to prevent any accidents or incidents as the aircraft is coming in. There's times when aircraft might have a missed approach or may have to take a hard left turn to avoid an aircraft that may have tried to cross on a taxiway or crossed over the runway. So they want to make sure that space is clear of any object, any trees, any light poles, any power poles, anything like that. So that's why you see this isometric drawing with these different these shapes and spaces on them. So it is a challenge because you really have to not mostly thinking of flat work. You're thinking in a 3-dimensional space when it comes to the approaches to the airfield. Here again, it's just kind of a little more detailed look at section of what some of these spaces look like. For example, you've got the right side of visual runways, and runways not lower than what they call 3/4 statute miles. So When it comes to approaches, you have to worry about, of course, cloud cover, weather, fog. So these are for runways where where you cannot see the visual, 3/4 of a mile away from you. So these are kind of what these surfaces would look like as an imaginary surface of the aircraft is coming in. In the 5313, the FAA has this nice little chart that they've done with this, and I appreciate that they've improved this, because I do remember designing and having to actually physically draw these charts out to figure out my runway lengths and widths and safety areas before the runway and after the runway. Now we're fortunate enough just to be able to know what our airport approach category is and our design group in, and kind of plug that in, and it drops and populates these numbers for us in the chart, which is much more much easier than what I used to do in that tedious operation. So as you can see here, for example, this is what we call the AAC and C, D, and E. It's group 4, which is some of your larger aircraft. Runway widths are around 150 feet wide, and then we've kind of get into the shoulder widths that are required, the width of blast pads, which is the areas before and after the runway that are paved, just to help control any foreign objects from being on the runway or dropping on the runway and being picked up or sucked into the aircraft. We also talk about the RSA, which is called the runway safety area. This is the area that's beyond the ends of the runway and also run parallel to the runway, on the left and right side. You can see there, for this case, this is 1,000 feet. So, we want to make sure that nothing before the runway 1,000 feet or after the runway 1,000 feet is there that is not what we call fixed by function, which means it has to be a frangible, like a light, approach light, or an instrument landing system. Those are items that are fixed by function. They're frangible. So an aircraft did come in short and a wheel gear caught them, they would easily break off and reduce any potential damage to the aircraft. Or if it landed long, it would skid off towards the end of the runway and be able to knock those lights over easily, with, again, not causing too much damage or any damage to the aircraft. So these charts have really been handy to us here lately, and I just love them. Here is a drawing, what we call an airport layout drawing, and this particular drawing here is of Bush Intercontinental. As you can see here, it's a little tough on this picture, but I think the next slide shows a little bit better. I wanted to kind of give you guys a visual of that isometric drawing I showed you a little bit earlier. As you can see, this is kind of you can see this where it says part 9, part 77 approach surface at 50:1. That is that approach surface that you kind of saw as you looked at the drawing, as went from basically from left to right on that previous drawing. So this is the trapezoidal approach surface. This drawing here, purple, you can kind of see, and blue, you can see the runway object free area. The blue line is at the runway safety area, and the blue area is the runway object free area around this particular runway here at Bush. So again, these are all areas that we are trying to keep clear of anything that to penetrate them, unless they are fixed by function like a light. When it comes to grading, we've got to be very exacting as well. The aircraft are not like most of our passenger vehicles. They don't do well with abrupt changes in grades. So our runway profile here, you can see that pretty much the first and last quarter of the runway are fairly flat. We want to make sure that the aircraft comes in on a nice smooth straight surface, and then from there we'll have large vertical curves if we want to make changes to the runway. And a lot of times it's like in highways, it's really kind of governed by the terrain you're given. How much fill you need to put in there. If you're trying to conserve fill, you can put some of these larger vertical curves in to provide that smooth transition from one to the other. But again, it cannot exceed that 1.5% in this case for category C, D, and E aircraft, which is the larger aircraft on the profile. So Most people like to have those runways nice and flat and straight. We do our best in that, but of course, like I said, it just depends on what you're giving out in the field. But we do have some flexibility in making those changes. Transverse wise, it's kind of the same thing here. We have our runway here on the right. We have our maximum transverse slope is typically for a C, D, and E aircraft is larger. You're going between 1 and 1.5 on the pavement itself. On the shoulders, which is shown in like S2, that could go from 1.5 to 5%, and then after that, it's usually 1.5 to 5% here in the turf area. So again, fairly flat. We want to, of course, propagate getting water and anything else off the pavement. So we want to have that percent just to make sure we got positive drainage everywhere and getting the water escaped from the pavement, but also making sure that's a smooth surface for the aircraft to land. Again, they don't have the same capabilities as our vehicles do. And you guys have probably felt it sometimes when you have a pilot hit a hard landing. This drawing also shows what I was just talking about earlier on some isometric drawings and in the chart as it projects the runway safety area here in this case. And it's going to be anywhere from 250 feet from center line, so 500 foot total width here, and this could be 800 feet wide here on the object-free area. Again, anything in here is really affixed by function, such as an edge light or a center line light or a threshold light. So it has to have a purpose in order to be within the area. Same goes for the taxiways as well. We're designated taxiway safety areas, taxiway object-free areas. These are, of course, are a little bit smaller because you're not at the same speed as you would be as you're coming into a runway. So these can be a little bit smaller because the aircraft, the pilots have a little more time to react to any changing conditions in the field. Here again is a typical kind of layout between runways and taxiways. This here will have the separation. For example, at Bush, there's a lot of taxiways have at least 400-foot separation between runway and taxiway center lines. Again, you see this trapezoidal area here, which is the runway protection zone and approach surface. Another dashed line here indicates the safety area, the runway object-free safety area. A solid line is the runway safety area. So we've got two areas there to keep clean. In the middle here, I think this was just reserved for any apron type of work, or some airports like DFW will have parallel runways either side and the terminals are in the middle. So this what this kind of blank area represents. Taxiway design, same type of charts. Is not as intuitive as the runway charts are, but kind of found on those same lines when we're getting into the airplane design group. Again, we have 6 categories here, but we also have another 7, or actually, was it 1A and 1B? So essentially 8 categories when it comes to the taxiway design group. When we're talking about the width, the safety margin, and shoulder and distance between a taxiway, taxi lane, center line, and another taxiway or taxiway center line. So these are all, again, based on the characteristics of an aircraft. When you're designing taxiways, a lot of the work there is just basically consider yourself in the car, and like you in your car or in an aircraft, cockpit over center line. The pilot's following that center line because he's in the cockpit, so it just makes sense. It's always a cockpit over center line. You want to make sure that he's following the route that you give he or she through the airport. Different sizes, taxiway safety areas, different widths of taxiways here, from the smaller groups, your 25 and 35-foot widths, 50-foot widths. These are mostly your general aviation airports, airports like Huntsville, airports like Sugar Land, airports like that. Then you get into the larger groups here, where you're going anywhere from 50 to 82 feet. And that's when you're going to get into your Love Fields, you get into your DFWs, your El Pasos, your Bush airports. Most of the time you see these airports will be around the 75-foot mark when it comes to the width of the taxiway. And that's kind of, again, based on the gear configuration that we had in this drawing here. As you mentioned here, we have the wheelbase, the cockpit to main gear, the length, and the main gear width. There still is a chart for taxiways, as you can see here. So as we mentioned before, this is the cockpit to main gear. So essentially you're coming through this chart in feet. All right, this is my aircraft. It's coming in at 50-ish feet. Its main gear width is X number of feet. And you say, okay, I've got a taxiway design group 3, or I have a taxiway design group 5, which is, these larger aircraft, such as your cargos, 747s, that sort of thing. So um, fairly intuitive, fairly, not too much rocket science going into this one once you know the characteristics of your aircraft that are serving that airport. So, and that's usually always a big key, is getting with the airport, knowing which aircraft are going to serve, or which aircraft is going to be the most demand for that airport. Here are kind of some typical taxiway designs. The one on the left is an entrance taxiway. This is an entrance taxiway onto a runway. As you see, it's kind of a really hard geometric shape that had recently changed over the last several years as the design manual has changed to 5313. That used to be kind of a smooth or curve, but we noticed that there was always a issue with pilots because the runway and the taxiway kind of can look similar, especially in lower visibility weather. Even though you'll have a white runway lights on the runway and blue on the taxiway, sometimes during the day you don't see those lights as well. A pilot doesn't see those lights as well. And with both of those pavements kind of being squared off, there's been issues with pilots actually landing on taxiways. I've actually had it happen myself on construction. It was about 10 feet above my truck when he came down. So that was a very interesting day. So with some of these incidents, the folks at the FAA say we really need to change this up, and that's when they've kind of gotten to more of the curved design for the taxiway with the hard geometrics on the inside. And the idea is that to keep the wheel gears out of the turf. So there's always what they call a taxiway safety margin, which is usually around 10 to 15 feet from the outside of the main gear to the edge of the pavement, just to make sure that even though a pilot's following that, his cockpit over center line, it's following his center line as he goes out there, wants to make sure that gear does not drop off in the turf and really just stall him out. Because if it's a soft day or their ground is soft after a heavy rain, it takes a really big tow truck to get some of these aircraft out. Believe me, I've seen it happen where the smaller Air Force One got stuck in Champaign, Illinois, and it took quite a bit of effort to get them out of the turf that day. The second drawing is more of as the high-speed taxiways. You see those more, like I said, at a DFW or a Bush airport. These are just to expedite aircraft coming off the runway as fast as possible, but also being able to be under control the entire time as they are exiting the runway. These especially for busy days when there's a bank of flights coming in. As mentioned, O'Hare, you're looking at 900,000 flights a year, just 2,400, 2,600 flights a day that they're landing and taking off. So they want to make sure they can get the runway cleared for the next aircraft to come in. So the high-speed taxiways is the typical way to do that work. The next drawing is just kind of an example of a turning movement here. I think this is a group 6 here that worked with my friends at Burns and Mac. We got a project at Bush, so they put this together as part of our design. Got to give credit to the folks I work with because like those guys. So I want to make sure that we're all stay recognized here. So this is it's like a group 6 here at Bush, and you can see kind of the turning movements as it comes off the inner taxiway and as it proceeds towards the terminal. What you see in red is the area that we want to keep clear for wingtip clearance. The center line we have in this case is a solid, is the red line. And then we have the kind of a blue lines, which indicate the outside of our main gear. The goal here is just to make sure that we are meeting that taxiway edge safety margin. And kind of some of the things we do with these simulations is really kind of lay out our phase areas, during construction. We want to make sure that we are meeting the standards for aircraft to pass by us, while the contractor is working to keep everybody safe here. We're kind of laid out the phase areas here along the taxiway object free line. Again, this work we're doing out at Bush, and this kind of I work with my friends at Jacobs here, on this work here. So we can see we've laid out the phase areas, following the taxiway object free areas, and what we've done in this case, we did model it with the model you saw before, just to make sure that taxi lane RB, we can pass aircraft through without an incident or accident occurring. Theoretically, it's always up to the pilots to make sure that they're following the path that we give them. So these are very useful tools that we use as part of our airport design. So we talked a little bit about geometrics. We talked about runway, taxiways, and how those are done. So we kind of get into the pavement a little bit. So our typical pavement structure here for an asphalt and concrete. You see we have an asphalt surface, stabilized base. Kind of similar to what goes on to some of the highway pavement. It just depends really on the weight and the number of repetitions an aircraft comes into a certain airport, the aircraft mix. Here, a typical design is based in what the FAA calls their far field program. So it's a layer, elastic analysis of pavement. And essentially what you do on the right side, you can see at the very bottom, we input all the aircraft that are known to come into the airfield, their weights, average weights, their number of departures, any expected growth that might come from that aircraft, and it kind of generates what they call the cumulative damage factor, and analyze each one to see which one is really the worst. Really, kind of back in the day, some people thought some people are not familiar how it works, that hey, we've got these large aircraft, they're near 1 million pounds, but they've got all these tires on it. Well, that helps to help distribute the weight, so that reduces some of the cumulative damage factor. It's also based on some tire pressures. Like F-16 has a high tire pressure, can do more damage than some of the larger aircraft. We used to call the 727 aircraft the pavement buster, just because it was just two wheels and the main gear on each wing. It's a dual wheel configuration, but because of the weight of it, the amount of pressure and pounding it put on the pavement, it was worse than some of the larger aircraft, the 737s and the newer models. So it was infamously called the pavement buster, just because of what it did to the pavement, the damage it did to the pavement as it kind of accumulated in and out of the airport. So this program analyzes the traffic mixture. What the base structure is, which I showed on the previous slide, was kind of the base structure, and we were able to go through and manipulate some of the layers based on our location here in Texas. We can't get a lot of what they call the P209, which is the crushed limestone. It's just not as prominent here as it would be in the Midwest, so we have to kind of make some changes to what type of stone we could use sometimes to be more efficient, but still meet the required pavement design. Here, for example, is just again a list of the layers and thicknesses that the FAA puts out. P401 is the asphalt, P501 is the concrete. As you can see here, quite a few different surfaces that we kind of mix, use a mix and match to help provide us with our available materials, but also meet the FAA's pavement design. This is kind of divided up again into 3 different regions here. Anything that's less than 60,000 pounds, basically, and then anything 60,000 to 100,000 pounds, and anything over 100,000 pounds. Each has its different requirements, both for asphalt and for concrete surfaces. Next slide. We have our runway and taxiway marking. These aircraft, we got to put them down somewhere. They've got to be able to visually see what's going on. So we have our runway and taxiway markings here. You can see The runway are typically in white. They are divided up into what they call non-precision and precision marking. Precision markings have uh, visual cues roughly at every 500-foot intervals as an aircraft approaches. As you see there, you have runway 9. It's got 3 bars on each side of center line, then has the main bars, and then you see a set of 2 more bars and 2 more bars, and this kind of proceeds down the runway as if it is a precision runway, and that's precision runway is determined by its approach, and a lot of time that has to do with the instruments to it. So you have a glide slope, which is an indicator of how the pilot is approaching the runway, and the angle at which they're approaching runway, and the localizer, which is basically send out a signal to the center line of the runway. So in the cockpit there, if the weather minimums are down or the weather is bad, they know that, hey, I'm coming in at 3% on this. I'm lined up with the center per the localizer telling me here on my dash here, and the same with the slope. So they are identified also visually by the markings on there. Non-precision runway is typically you have your threshold, your landing bars, and then that's really it. On taxiways, it's all in yellow marking can also have signage that's also painted on the surface. Anything that has a red background with white numerals is usually just like us. It's a stop. Can't go any further without any permission. Anything with a black background with yellow numerals is a location. Anything on a yellow background with black numerals is a direction. So you can see there in the right side, we have our yellow center line. We have our surface painted signage. You also see a double yellow line followed by a double dash line. That is called a hold position markings, which indicates that there's a runway there, so that the pilot will have to hold until he or she is cleared to cross the runway or proceed on the runway for takeoff. Typical airport lighting, as mentioned before, runway lights are white, taxiway lights are in blue, so we help determine that. A couple of nuances as you approach a runway, the lights there on the threshold are green, so that you know that, hey, I'm coming to the approach of the runway. And usually on the first 1,000 feet as you approach the runway, you'll see the white lights. Now, if you're coming the opposite direction, say in this case, as a person's going from right to left on runway 20 there, they would start to see yellow lights as they got to the last 1,000 feet of the runway, and let them know, hey, I'm coming in to the last 1,000 feet. I need to make sure I get up off the ground or abort my takeoff. And then at the very end where the threshold lights are at, you will see those in red if you're coming the opposite direction. There on the right is just an example of the spacing of the taxiway lights, which, like I mentioned before, are in blue. Most runway lights, 200-foot spacing. Taxiway lights can be at 100-foot spacing. It just depends on how much straightaway you have. Do you want to evenly divide the lights as you go down there to lay those out? And as you come up to curves on lights, you'll end up having more lights on your curves for taxiways. One light will indicate this is the beginning of the curve or the PI, and then as you go around, you'll shorten your light spacing up depending on the radius of that curve. Other lights, airport lighting system. This is an example of a Category 3 approach. You can see there's lights everywhere as you're approaching that runway. We have a long threshold bar. You'll see the white lights at the center. Those are center line lights. On the outside, you kind of see these red lights on either side. Again, that's the touchdown zone lighting as you're coming into a runway, and on either side of the runway, you can see the white lighting. On the right, it's kind of just an example layout. The first few single lights are called the sequencer flasher or rail lights. So these lights are geared in such a manner that the lights flash in sequence to lead the pilot towards the end of the runway. And then the other lights are the approach light system here. It's just our steady burn approach light array to let the pilot know, hey, you're getting closer to the end. You see the 3 bars there, which indicates you're 1,000 feet from the end of the runway. And then, of course, as you hit the runway, you'll see the center line lights and then the touchdown zone lights as you land on the runway. As I mentioned earlier, a couple different systems for instruments here on the left. We see the 747 there landing, that little orange and white checkered building with the tower next to it. That is the glide slope. Again, that refers to how much the angle of descent for the aircraft is coming in, usually about like I said, around 3 degrees as it comes into the runway. And there on the right is the localizer. Again, that helps the pilot align to the center of the runway. Again, these are items that are fixed by function, helps to allow aircraft to come into the runway when the conditions are a little bit worse than your regular sunny day. And I think with that, I'm on my last slide. So it gives us, hey, it's about a little over 10 minutes or so for questions, and just kind of one of my shot at the highway people. Even though I love you guys and gals, a mile and a half of highway will get you a mile and a half down the road, but a mile and a half of runway will take you most anywhere in the world. So with that, in my presentation, we'll throw any questions out you guys might have.
Jason, there were several questions in the question and answer box. So if you want, I'll just start reading them off to you.
All right, let us rip, Ron.
All right, question one: how often do the airports need to be updated to meet FAA requirements?
That depends. The FAA standards, the 5313, they're actually getting ready to publish a new one here shortly. But before that, it was, 15, 20 years before they had updated some of those standards. Now, in the interim, they will issue like a technical memorandum or technical letter if they see a potential issue with pilots, or if there's what they call hotspots in some places that are popping up in a lot of airfield because incursions. There might be some confusion on whether this taxiway alignment is correct, or how a taxiway comes into a runway. So again, they don't update it too often. They have more recently, just for safety. Before, there was always a conflict between the FAA and the ICAO standards, but I think now that they've become more aligned as in the way that they are doing their designs and requirements now. So again, not too often on 5300, but if there is an issue that comes up, then they will issue a memorandum or a letter.
Okay. Next question: why did the FAA separate ADG and TDG?
Again, that kind of goes to safety. They were trying to once kind of group them all together, but now they've kind of split those apart in order to make sure that they are meeting both the runway and the taxiway standards. Before, honestly, the taxiway standard kind of lacked, and you did see a lot more of the main gears kind of dropping off on shoulders or into the turf or things like that. So that's why I say we need to really kind of split these up, because different aircraft have different main gear and widths and different distances from the cockpit and from its own nose gear. So that's really the reason they really had to split these up. It's two really kind of different animals you have to deal with.
Okay, next question: how often do airports have to adjust runway designations due to magnetic variance?
I honestly haven't seen it too often. I think in my 20-some years, I've seen the runway adjustments once, to be perfectly honest with you. Yeah, it depends on where you're at. Some places, I don't know, have a different mojo or juju or whatever you want to call it when it comes to the magnetic declination. I lived in Arizona for a while, and they always thought up in Sedona, it had a special place with different magnetic fields. So it just depends on how often they go out and verify that they still are the correct designation. But I've only really seen a full airfield change out once in my career.
Okay. Next question. This is one of the largest lists of questions we've had in a while, so this is good. What is the code for design of airport runways?
What is the code? I guess I'm confused on that question a little bit. As far as I guess a little, yeah, I'm a little confused on that one.
Yeah, that was entered in, and if the person who entered it could go ahead and add some clarification, that I'll go on to the next one and we'll come back. Which software gives accurate design for airport runways?
You really have to stick with the FAA design when it comes to the airport runway. So along with the 5313, you kind of get some companion software that the FAA puts out, and a lot of this is run through 99% of it is run through their FAA technical center that's out in New Jersey, and plus the folks in Washington, D.C. that go through and go through the process of designing these programs. There are, what they call second or third party programs that we use inside AutoCAD, like with our group. There's a program called Aviation, which I think is similar to the turning program for vehicles. It's just used for airports, and this is what we kind of use to verify some of these programs that the FAA puts out, and also we can use it in the case because you see some of these TDGs are so broad when it comes to the tail heights or the gear widths and stuff like that. So there's a lot of aircraft that can fit into that one location. But if you have an airport that doesn't see 90% of some of those aircraft, they only see one type of aircraft, for example, left field, it's a lot of just 737s. I mean, so this is pretty much the same aircraft. You can take that program and kind of tailor it more towards that airport to try to save some pavement on taxiways, because you just don't see it. If you have this airport that says, yeah, we get one of that aircraft every once in a while or every in a blue moon, but then you have to build a 75-foot taxiway for it, and you say, oh, we can't do that. We need to get it down to a 50. So that's why it's handy to kind of have a program like Aviplan to kind of justify reduce the pavement and the costs.
So this may go with maybe a similar question, but what software do you use for the turning movements?
Yeah, that'd be an Aviplan. We're using the base design in FAA, and it'll have the radius, both inside the centerline radius and outside radius, like we saw in that one drawing. But we also can use the Aviplan software to help verify those turning radiuses and movements.
Okay, now I did not get any clarification on that previous question. So unless anyone has anything else, that is the list of questions we had. I don't see anything else popping up. So, oh, here we go. This says, being an airport, trying to increase, being an airport engineer, do you get to be on airports a lot?
Yeah, and it's fun. Let's just say it that way. Yes, I do. Yeah, we get to, we're out there, we're driving the runways, we're walking the runways, we're walking the taxiways, especially when we're doing pavement inspections, we're looking at that stuff. If there's an issue with turning movements or things like that, we're examining the way the taxiways are designed and built, taking measurements. So yeah, we get to be on the airfield quite a bit with moving aircraft around us. On aprons, it's not too bad, but it gets quite a bit busy when you're out there on the taxiway or the runway and you're having to deal with the FAA control tower to make sure you keep yourself in the right place and not getting run over by an aircraft, especially at night. Even at Lambert Field, I had a UPS pilot think it was pretty funny to not run around without any lights on until they got close to us and then flip their lights on out there while we're doing a pavement inspection. So
nice. We did get one more question pop up. Are there any technical books or manuals outside of ASCE's you would recommend?
There was an airport design textbook because at University of Illinois we had a textbook for the class. I don't know if they still print it. I still have my copy of it that is now 30 years old, but it's called Airport Engineering. If you can find a copy of that book, that's always good. There's not many colleges anymore that have a class on just specifically airport design. We're civil engineers. I consider us the Swiss Army knife, all the engineering community, because we could do so much with what we study and what we do. So
absolutely. Jason, I don't see any other questions or comments in here, so I'm going to go ahead and thank you for a very interesting presentation. I'm sure you could talk for hours on this, and I'm guaranteeing it was a challenge trying to condense it into an hour.
Oh yeah, we could. Yeah, so most welcome. I hope everybody enjoyed it. Just kind of got a basis of what kind of goes into airport design. Things that we're looking at. The technical manuals we have to use. So hopefully you enjoyed it, and if you folks want to give it a try, feel free. If you're your company, your group has an airport group, hey, ask them to do a little design work for them, and